Thank you. Thank you all for joining. And yes, I need to first. Uh, so this is the first part, kind of the first part of what we've been up to. This is the elicitation stage of an entire lengthier process. Now, it started off as something that was more focused on VR, but at this point, it kind of drifted off towards concert hall acoustics, and now we're pulling it back towards VR. We have a preprint available now on archive, and any feedback on that is extremely welcome. We are looking forward to publish it soon. But yes, this presentation is going to be about the listener position and orientation dependency of the auditory perception in an enclosed space. Now, I'm going to start with a little bit of background and just a little reminder about spatial impression, and that in a concert hall, the spatial impression is a broad and it's something multi-dimensional. It's a subjective experience. And very common up to this day is that we have this spatial impression that is comprised of two elements, mainly two attributes, which are the apparent source width and the listener envelopment. Now, these have been around for about 20 years now, more or less. And they seem to be limited in some regards because most of the research does not take into account the head orientations. Now, again, this is because in terms of concert hall acoustics, we are not concerned about how the position in the hall affects the perception, but we're talking more about how different halls compare to each other and which halls subjectively sound better or worse. Now, another problem with this, the moment we change the listener position and head orientation, is that we might introduce new perceptual auditory attributes, which has been under researched by now. Talking about the aims, for now, the aims of this paper especially was to perform, the main aim was to perform an elicitation test, taking these multiple listening positions and head orientations into consideration. Now, another very important aim is to provide a set of perceptual auditory attributes which describe that concert hall. And the third aim would be to find the most salient attributes. So we give a set of attributes, but we also need to find the most salient ones, the ones that we hear the most in a concert hall. And we need to figure out what they are describing and what the perception of those salient attributes are. Now, the whole story starts about 1 or 2 years ago when we conducted kind of a pilot test. It wasn't really a pilot, it was still an experiment. It was, and this is all explained in the paper, but we had an in situ elicitation in our St. Paul's concert hall. And we also recorded an extensive set of BRIRs, ambisonic impulse responses with multiple head positions and multiple positions and head orientations. Now this will come in handy a little bit later. But this is a mandatory picture of me doing the measurements, and we also have a download link to that database. There are 1,700 impulse responses from all around the hall. We have 17 positions and 100 head rotations per each position. So I will make the slides available after the presentation, but if not, you can also take a picture of the QR code. And we will now slowly go towards the experiment and how the experiment was designed and how it was performed. Now, we used the repertoire grid technique as a methodology for for elicitation. This was adapted and proposed by Jan Berg and Francis Ramsey. And probably some of you know how this works and how they implemented it, and it's very similar to what they did. It is comprised of two stages. First of all is what they call elicitation by comparison in triads. Now, what the main question when performing this test is what do two of the stimuli have in common, and what they have different from the third one in terms of spatial impression. This was very important in our case because we were assessing the spatial impression. This is the first stage. The second stage, the result of this is called a bipolar construct. So for example, because we're doing it in triads, we can see what two of them have in common and what they have different from the next one. And we end up with a bipolar construct, which is something, for example, wide or narrow source. The second stage is a rating of each individual stimulus in relation to their own elicited, to the participants' own elicited terms on a scale from 1 to 5. Again, this puts the whole test into a more structured framework. We don't just ask people around what they hear and what it feels like, what the sound feels like, but we can also measure and perform some statistics on these results. Now, what I'm talking about now is a laboratory experiment. So we had the in situ experiment, and then we performed a laboratory experiment. What I'm focusing in this talk now is about the laboratory experiment, which was the one that was more important. We had 8 very experienced participants that took part in the test, and it was important for us to have a focus group, not just ask everyone around what they feel, but we wanted to make sure that the people that took part were very comfortable with the room and were very comfortable with spatial acoustics and concert hall acoustics in our case, because we performed the test in a concert hall. We had 10 listening positions from the St. Paul's Concert Hall, and the positions are this one. So you can see that we assessed both different positions in the room, but also different orientations. So we assessed with the head looking we assessed looking forward towards the source, and we assessed looking 90 degrees away from the source. And this was the case for all of the positions. One of them was looking forward and one of them was looking 90 degrees to the left. And then 2 of them were actually looking backwards. Now, going on to the experimental setup, this experiment was carried in our critical listening room, an ITR BS 11163 compliant room. The stimuli were created with the BRIRs that we recorded earlier for our BRIR database. We allowed head movements. This was very important for us to allow head movements, but we limited them to 7.2 degrees on either side. So we had around 14 degrees of head movement. These were obviously real-time head tracked, and everything was sounding really nicely. We allowed the head movements because we wanted to make sure we minimize back and front confusions, even though we actually had a picture of each of the tested positions. Now, why we provided pictures of the tested position, that was because we wanted to maintain the ecological validity of the experiment. We wanted the virtual experiment to be as close as possible to the in situ one. We didn't choose a VR headset because that would have made the whole testing, the whole experiment a bit more bulky and a bit more tiring. So this was the virtual experiment in a nutshell. It is way more detailed in the paper, but for the sake of this talk, I'm keeping it very short because I want to talk a lot more about the results. Now, an additional test that we did was an audibility test. So every participant elicited a number of attributes that they found, that they perceived in this test. Now, not all of the attributes were as salient or as perceivable. So for this, we actually employed an additional audibility test, which let us know which of the attributes were perceived more by our participants. Yes, we used the scores from this audibility test to filter out the most salient attributes, and we used a 100-point continuous internal scale with semantic anchors. The audibility test looks something like this. Now, for each trial, the participant would be presented with their own elicited attributes. So, for example, you can see here wide or narrow source width. This was something that one participant elicited. They could go and click on each of the positions in the room, listen to all of them, and on this scale, they would be able to grade how audible the difference, the magnitude of difference between all the positions would be. In terms of test results, we had 98 bipolar constructs. These were the raw elicited constructs from the elicitation process, and with the associated ratings for each position. We also employed a verbal protocol analysis and cluster analysis for evaluating the results. This is why the repertoire grid technique is such a great tool was such a great tool in our case, because it allowed us to use cluster analysis to see which positions, which attributes are similar. And finally, the attributes were filtered using the audibility scores. I know this seems a bit complicated right now, but here is a simplified workflow of the analysis. So we had the in situ experiment, which was in which we had the repertoire grid technique elicitation, and then for the analysis we used VPA and the raw data clustering. The laboratory experiment was the same. We had the RGT elicitation, VPA, the data clustering. Now, at this point, we did a validity check between the analysis we got from the in situ experiment and the analysis we got from the laboratory experiment. This was very important in order to confirm that the laboratory experiment matched the in situ experiment, thus the ecological validity was maintained. And additional to the laboratory experiment, we did this audibility test. Now, in this case, we had we got some verbal feedback from our participants as well, which allowed us to to group, to put the data into see the data in another way. And we also counted the number of occurrences of each elicited attribute. From there on, we calculated an audibility index, and finally, we classified all of them based on this audibility index. Now, a very important result was brought up by this position clustering. Because we could cluster because of the repertoire grid technique, we could cluster the positions from the room, which was very interesting because the clusters resulted from the laboratory experiment matched exactly to the ones resulted from the in situ test. So that means that the laboratory experiment backs up the in situ test, which also means that if we know this, that means we can, from now on, use only the laboratory experiment, because we know that it is ecologically valid and we don't have to rent the concert hall and we don't have to get the participants at the same time in the concert hall, which makes the whole logistics of doing an in situ experiment is much more complicated. So yeah, this validates the setup and the methodology, and we are now sure that the virtual experiment works. And these are the clusters that resulted in terms of positioning. Now, you can see here that the first three ones are the ones the closest to the source. A possible reason for this is that the direct sound overpowers all the other spatial impression attributes. And this is fine because the distance is not that great. It's around 2 meters from the source at this point. The back two positions, 3 positions, but the cluster, we have this yellow cluster, which is the position facing towards the source and the position facing away from the source. One of the most interesting results now is that we have the green cluster, which are only the positions facing 90 degrees from the source. Now, again, this might be because obviously you have the source coming from the side, and they are very different from the ones that you look straight to the source. But when we did the experiment, we were very careful to remind the participants to focus on the spatial impression attributes. So this is very, for us, this is exciting to see that these 3 positions are clustered together. And finally, we have these 2 other positions that are lateral, but facing towards the source. In terms of attributes, we have some very interesting results as well. Now, we combined clustering with the audibility filtering, and we came up with this list. We used the audibility index to cluster and group and come up with a set of attributes. These are more or less the raw attributes elicited by the participants. They're just filtered, they're just classified in a way that goes from the highest audibility index towards the lowest. And we kept it off at 50, which on our scale meant, if I go back, on our scale meant from audible upwards. Yeah, right. And based on this, we came up with a list of attributes. Now, some of them might sound new. That's because we are proposing a kind of a set of not new attributes, but some that might encompass some more in-depth attributes. So I'm going to go more in depth into each one of them. But again, something very obvious is the perceived source loudness. The apparent source distance, again, something very noticeable. So we have some new attributes, which would be the echo direction or reverb direction. But I'm just going to go more in depth into all of them right now. So the highest audibility index was this perceived source loudness. And this was expected because this is related to the SPL and consequently to the inverse square law. Now, another salient attribute was this apparent source distance. We call it ASD. And this refers strictly to the perceived source to listener distance. Now, again, this requires a lot more investigation, as the physical distance and the perceived distance might not be consistent. Some studies show that closer than 1 meter to the source, subjects seem to overestimate the distance, and further than 1 meter to the source, subjects tend to underestimate that distance. So we can see that the perceived distance is very different than the physical distance. And we can also see that the perceived distance might change as the head rotates. So we don't know yet if the perceived distance is the same if when the head rotates to one side or another. And I'm talking about this at the same physical distance. So at one position, when you start rotating your head, you might perceive the source at a different distance. And obviously the apparent source width, the classical apparent source width, but we expect this to be influenced by these aforementioned attributes, by the ASD and PSL. Older research states that this ASW might also be positively correlated with the sound strength, which is an energy measure. And because of this, the degree of source broadening was proposed, and this also uses both the strength, the sound strength G, and the lateral fraction. Now, IACC and lateral fraction alone are still successful in evaluating these different concert halls between them. And thus, we can hypothesize now that our elicited apparent source width might be comprised actually of two separate dimensions. And one dimension can be related to the direct sound and its strength. And this actually leads to the perceived sound, perceived sound level. No, wait. Loudness, sorry. This leads to the perceived source loudness. The second dimension is related to decorrelation and the lateral energies, this being fused with a direct sound. So it's important here to take into consideration that when assessing all these different perceptual attributes and at different head rotations, that we might have more objective measures being able to describe it. So for example, SW might be defined more by decorrelation up to one rotation angle, and then after a certain rotation angle, it might be defined more by something in the terms of sound of energy. Also, this is the case in terms of distance. So before critical distance, the SW might be defined by sound strength G, but after critical distance, this might be defined by something like IACC or lateral fraction or some sort of decorrelation measure. And this is just a little sneak peek from a paper that we presented last week in AES. These are the IACC measurements that we did on the same on the same results. This plot over here is the central axis. There are 4 positions on the central axis, and this is the IACC as a function of head rotation. All the other ones are lateral columns from the room. But what we can see in all these plots is this trend of having a slight peak when the head is facing 90 degrees in terms of IACC. And these are all aligned with the source. All these measurements are aligned with the source. So 0 degree on the plots means that the BRIR is facing straight to the sound source. But yeah, this is something very interesting that we found out, that between around 70 and 110 degrees, there is this kind of rise and fall of IACC, which needs to be investigated more. But this is something, again, this is explained more in that paper, why we think this is the case. But yeah, we're going back to the attributes elicited in our study. I'm now going to talk a little bit about some room-related attributes. And Francis Ramsey says about the envelopment, spaciousness, and spatial impression that anyone who attempts to wrestle with the semantics of these terms is to some extent asking for trouble. And guess what we did? Yes, we tried to wrestle with these terms, and up to some point we were I would say, successful. We obviously found listener envelopment to be a salient attribute. This was one of the most salient attributes. But again, this is a very multidimensional concept because it can be measured by both both uh, energy measures or decorrelation measures, such as LG80, ICC, L3. And this tells us two things. This tells us that we can have two possible sub-attributes elicited in this study. Now, we found that a salient attribute was this apparent reverb width. And this is possibly related to a late decorrelation measure, something like ICC L3 or lateral fraction, late lateral fraction. And what we know at this point from talking to the subjects and manually trying to go through the attributes that we got, the elicited attributes, we know that this is perceived as the spread of the reverberant sound. And this is linked to the room itself. This would not change that much. This is linked to the geometry of the room. The second dimension of listener envelopment, we think would be this perceived reverb loudness. And this might possibly be related to a late energy objective measure. Again, this is a very, very interesting attribute because all the previous literature, and this is something that we know for sure, that the physical level of the reverberation doesn't really change that much in a concert hall. It is fairly consistent throughout all the positions. But in our case, it seems to perceptually vary. Now, we believe this is the case because we have multiple positions and head orientations. And these positions changing positions, but more importantly, in our case, changing head orientations, might lead to binaural unmasking. And binaural unmasking would lead to a differently perceived reverb level. Now, the last attributes would be echo and reverb directionality. And we theorize this to be perceived as an effect of the different listening positions and head orientations. This is going back to the initial aims, where we were afraid that if we change positions and head orientations in a concert hall, we might introduce new attributes. So this came out as one of the new attributes. And subjects seem to perceive a directionality in the echoes or the reverb. So people seemed to perceive that the echo and the reverb was coming from a different direction, not necessarily enveloping, but it was coming from a certain direction. And the last one is the echo and reverb brightness. Now, this is normal, and this is a timbral characteristic of that's a typo, of the reflections or reverberant field. This was, I think, the easiest for participants to elicit because brightness is such a common word used in audio and audio perception. We can always say that, oh, that sounds bright or that sounds dull. This is kind of one of the easiest to notice in terms of timbral differences. And I will now quickly tell you some of the conclusions. We're rapidly approaching the end of this talk. It's already half an hour. So we, as a conclusion, we elicited a number of salient perceptual attributes. We extracted them from the two elicitations we had, and we used the repertory grid technique. We know that the results from both elicitations agree with each other and that is very encouraging. In terms of position clustering, the elicited constructs were filtered based on an additional audibility test that we could do because we employed a virtual experiment. Otherwise, we couldn't have done the audibility test. If we did the in situ, we couldn't have done the audibility test. So again, this is an advantage of using the virtual method, that we could do an additional audibility test. And we believe that the perceived source loudness and apparent source distance can influence the perception of the apparent source width. Not only that, but they might be two subcomponents of the apparent source width. We might have apparent source width as an umbrella term for these two more low-level attributes. And listener envelopment, we think, is comprised of two separate perceptual sub-attributes, which is the perceived reverb level and the apparent reverb width. Also, we believe that the perceived reverb level is affected by the directionality of the perceived directionality of the echoes and reverberation. In terms of ongoing work, we have to do some objective grading experiment in order to assess the relationship between the elicited set of attributes, this list that we came up with now, and the multiple listening positions across the room. Again, the elicitation doesn't tell us anything about the magnitude of which these effects happen. They just tell us that they happen and they are salient, but we need an additional experiment. Now, this experiment should have been done this summer, but again, we cannot really do it for now. So we expect to do it when the world opens up a little more and we can get subjects back in our listening room. But since then, we started calculating a number of objective measures, for example, IACC, lateral fraction, sound strength, all these objective measures using our BRIR database measured last year. And we already have a publication. We published this last week in AES, and we are there talking about this variation of IACC across multiple positions, multiple head orientations in this room. We want to find a correlation between the objective measures that we will measure now and the experimental results from the grading experiment that we will probably do this year. And we really want to measure some BRRs in smaller rooms. We did this in a big room for now because this is where the spatial impression really comes to life and is really evident. But we want to see if these attributes are also perceived in some smaller rooms, like, for example, a classroom, or maybe even smaller than that. And ultimately create a perceptual model of that room based on our experimental results, and test that perceptual model of the room with a final objective experiment. And with that, I want to thank you so much for listening. I know it's been probably a bit long, but in a nutshell, this was our latest paper. It's still a preprint, and again, any feedback is welcome on that. This paper has a lot of detail about everything that I talked about in this presentation. So yeah, thank you.